Hi, everyone. I'm Chris Klepper. I'm a program manager with the Azure Blockchain team. I've got today with me Sylvan Klepsch with Microsoft Research, who is one of the founders and developers for what we call Ccf, the Confidential Consortium Framework. Thanks for joining us today, Sylvan.
I'm happy to be here. Thank you.
So let's talk a little bit about Ccf. So we know it's open source and live on GitHub right now.
That's right, yeah.
It has a lot of very interesting nuances to it, but let's go ahead and start simply at the top. Can you just give us a very basic description of what Ccf is?
Sure. Ccf, the reason it's called the Confidential Consortium Framework is it really is intended as an SDK for building out confidential blockchain-like scenarios, so secure multi-party computation scenarios. So it's an open source framework that leverages trusted execution environments and provides consensus, distributed ledger technology, confidentiality, and integrity, all in a package that an application developer can use to build out a confidential distributed application on top of the framework.
And then if we contrast that versus the current state of blockchain?
Sure. So blockchain has a lot of really exciting guarantees. The tamper-proof ledgers is, in some sense, the core of it, but the cryptographic chaining, the key to the cryptographic chaining, to my mind, is that it establishes a total order of events. So it tells you what happened in the order it happened in. And that's incredibly powerful. And it's not just for cryptocurrencies, right? There are lots of different scenarios that can be enabled with this kind of distributed ledger technology. But then on the other side, there's some core problems. Now, these aren't problems in the sense that they're problems for decentralized public blockchains, but they are problems for enterprise-grade distributed ledger technology. And one of the key ones is power usage. Essentially, existing approaches demand a lot of power in order to enable Nakamoto consensus, or what's called proof of work, or even proof of stake models. And on top of that, determining if a transaction is successful because of the way that chains fork when using proof of work or proof of stake, determining if a transaction is successful is entirely probabilistic. There's a sort of a rule of thumb that you wait, roughly speaking, 6 blocks, and that radically increases the chance that your transaction becomes persistent. But there's no guarantee ever. In addition, transactions aren't confidential. There's an idea that blockchains provide anonymity, but they don't. They provide pseudo-anonymity. And what they do is expose all aspects of a transaction, but not necessarily personal information about who is performing this transaction because of the way that Bitcoin and Ethereum addresses and things like that work. But what we want to provide is actual complete confidentiality of transactions. And then there's governance issues. Governance issues, folks might be aware of the various hard forks that have happened, or rollbacks for example, when the DAO attack happened on Ethereum. These kinds of things can be coped with in a public setting. All these things have been coped with. But in an enterprise setting, you need a lot stronger technical rule keeping for this kind of stuff. So this is really exciting technology, but we really feel like there's some key elements for an enterprise grade application that aren't really present at the moment.
And if we get into the value of building on Ccf.
Sure. So Ccf's intended to provide this high throughput and low latency so that it's competitive with a database instead of being competitive with an existing blockchain technology, and provides confidentiality in all 3 states in some sense. Confidentiality at rest, so that your data is encrypted when it's stored. Confidentiality in motion, so your data is encrypted during communication, but also confidentiality during computation, so that your data is encrypted while it's being operated over. And combining that with these contracts for governance, it gives you some really nice guarantees. And it's built on this idea of remote attestation, which maybe we can cover in a little bit. So some of the things that we're able to do right now are run about 50,000 transactions per second. That's for a straightforward transfer scenario. Maybe that's not running complex contracts, but it is in some sense a nice peak with latencies that are in tens of milliseconds. And that's for deterministic commit. So you know for a fact that your transaction is committed, and it provides full confidentiality, provides the governance, and we're maintaining, of course, the key properties that we love out of blockchain technologies: integrity, resilience, accountability, the things that we expect out of a distributed ledger technology.
Yeah, and Sylvan, you mentioned some of these scenarios specific to blockchain. So it sounds like with Ccf, the intent isn't to be really a ledger or blockchain implementation itself. It really can be an enabler of existing blockchain technologies.
That's right. And sometimes that's a little bit of a tricky message to get across. We're not trying to put CCF out there to compete with ledger technologies. We're trying to put it out there to provide a basis for turning technologies into high-performance confidential implementations. So it provides the groundwork for this. And it does that by providing key pieces like the consensus protocol and the key value store and the communication mechanisms. But the idea is that folks like JP Morgan, for example, can come along and extend their existing implementations using CCF to make these interesting new guarantees at the bottom of the stack.
Okay, and lastly, we keep talking about confidentiality and confidential computing. Can you tell us a bit just about how that works within the CCF stack as well?
Yeah, absolutely. So CCF is built on top of this idea of using trusted execution environments, where a trusted execution environment, generally speaking, is a hardware implementation, although there are software implementations, like there's a Hyper-V mode called Virtual Secure Modules that allows a software version of this with a different guarantee. But we're targeting Intel SGX for now, which is the Intel Software Guard extensions, which provide an enclave on the chip where all of the data is encrypted and integrity protected at the hardware level, including during computation on the CPU. And these hardware enclaves mean, like in the diagram here, that the application is completely isolated from the operating system, the hypervisor, and even from hardware other than the CPU. So that if someone were to compromise the operating system, compromise the hypervisor, the trusted execution environment would still be secure. That's pretty powerful stuff, but it really starts getting exciting when you can talk about how remote attestation works. You can get a cryptographic proof called a quote that a specific piece of code is running inside the enclave, and with CCF, you can extend that proof to say that all nodes in the system are running the correct version of code, and that you're absolutely communicating with one of those nodes, and that your encrypted session, your TLS session, actually terminates inside an enclave so that it's not observable even by a compromised operating system.
Thanks, Sylvan.
Sure.
So for our audience, please stay tuned for part 2 of this session where we do a deeper dive into some of the technologies at play with CCF. And appreciate the time today, Sylvan.
Thank you very much.